What's up, CoderByte? Welcome back to another data structures and algorithms video. I'm Elizabeth, and this week we're back with our regularly scheduled graph content. If you're not as excited as I am, which I can't imagine why that would be, let me entice you with this week's problem. You are given a network of nodes modeled as a graph. Some nodes are initially infected with malware. The malware will spread from the initially infected nodes to all of the nodes it is connected to, and it will continue to spread across the network accordingly. We have the opportunity to remove exactly one node from the initially infected list, which will remove it and all of its connections. Return the node that, if removed, will minimize the number of nodes ultimately infected in this attack. Now, this is a really cool problem in my opinion, and I think I like it for two reasons. I don't know if you guys know, but during my day job, when I'm not making videos, I actually work at a cybersecurity company. And this is something we actually do pretty regularly. We quarantine what we call endpoints, or which are computers, printers, whatever, on a network, right? If we sense that there's something nefarious going on, if there's malware, ransomware, whatever is happening. Now, we don't want to take down the entire network, right? Because at the end of the day, our clients are businesses. They want their computers to be up and running. And just because there's ransomware or malware on one of them doesn't mean we want to wipe out their entire network. So we want to be sure that the computers we're targeting are the ones that are the most meaningful to stop the attack, and we don't quarantine anything unnecessarily. So I personally really liked this problem when I saw it. I was like, aha, something actually useful. I think the second reason I like this problem is you can solve it in a lot of different ways. When I was researching this, I actually found many different solutions. The one I actually picked because haven't heard of those concepts before. And I felt like I wanted to really learn something new. And I was really curious about that solution over some other solutions that use the traversal methods that we've already talked about in previous videos, like depth first search or breadth first search. So I think that, again, take off that anxiety hat and let's put on that curiosity hat. And we're going to go through what I consider to be a little bit more of an advanced way of solving this problem. We're going to do this video in two parts. The first part is going to be introducing some of the concepts that we're going to then use in our second part when we actually solve this problem. So I hope you guys are as excited as I am. Let's get going. Okay, so in case you didn't catch all of the, text on the screen that was just there, let's go over what this problem is actually asking. So we're going to get a graph, right? And the graph is going to be basically each node is going to be something that can be infected by malware, a computer, a server, whatever, it doesn't matter, right? And besides for the actual, graph of the network of computers, we're going to also get a list of initially infected nodes. These are the nodes that there is definitely malware on, right? So in this case, we have this graph, we have some nodes, we have the 0th node, the first node, the second node, etc., right? All of these are nodes that could potentially be infected. And we have these initially infected nodes, right? So our first nodes that definitely have malware on them are going to be 1 and 2, right? So let's see that here. Okay, so we have our nodes and we have our initially infected nodes, right? So according to the problem, the malware spreads from the node that has it to all of its nodes that it's connected to, right? So let's just watch that happen, right? So if we get infected initially 1 and 2, the next ones that get infected are 0 and 3, and then from 3, 5, and 4 get infected, right? And that's how the malware spreads throughout the network. Okay, so essentially the problem is asking, out of the initially infected nodes, right? So in this case, that would be nodes 1 and 2, we're allowed to remove one of them. Which node, if we remove it, will have the biggest impact on the health of the overall network, right? Another way of saying that is what node, if removed, saves a bunch of other nodes from getting infected because they're no longer connected to any of the nodes that were initially infected by malware. So let's, for example, let's try and remove 1, right, and see what happens. So we remove node 1. So what happens? 2 is still infected, right? So first 3 gets infected, and then 5 and 4 get infected. But 0 gets saved because we got rid of node 1 and all of its connections. And so 0 kind of is on its own. We don't have to worry about it anymore, right? Okay, so let's put it back to how we originally had it. What happens if we remove node 2 now? So let's watch. Okay, so node 1 is still infected, right? And then 0 gets infected. But 3, 4, and 5 don't get infected anymore because they're no longer anywhere connected to that initial node, right? So which one would we want to remove if we can only remove one of them? Obviously, we want to remove node 2, right? Because that's how we save the most nodes. So just to, illustrate the problem for you a little bit more so you understand exactly kind of how we're going to be thinking about this. So we're going to solve this problem using a concept called disjoint sets. So what are disjoint sets? Disjoint sets is really just a fancy way of describing different nodes in a graph, this is a mathematical concept, so I think this applies outside of graphs as well, but in our case we're talking about nodes in a graph. And it's a way of organizing the nodes in components, and the components don't have any connections between them. That's what makes them disjoint. So, again, this is useful for keeping track of groups of elements or components of a graph, right? So in our example we just went through about what the problem is asking, when we remove that node 1, let's say, right, we have one component, which is 0 up at the top, and then we have the rest of the components, right? Or the rest of the other component, which is the rest of the graph. Just to kind of get you thinking in terms of how this concept relates back to the problem. So disjoint sets, again, it's disjoint when there are no connections between certain components, right? That's what the word disjoint means, is that there's an element of separation, which is what is meant by the different components of the graph, right? They are different components because there are no connections between them, if that makes sense. Generally, with disjoint sets, you're going to hear 2 methods thrown around. These are the 2 methods that you're using on disjoint sets. Okay, the first method is called find, which is essentially just given a node, find its parent, which is, the node of what component it belongs to. And every node in a component will have the same parent. So find is a method, given any node, give me what component it belongs to or what is its parent. Union is a way of taking 2 disjoint sets, remember the sets are not connected, that's why they're disjoint, and joining them in such a way so that they are now part of the same component, aka now all of those nodes that were once upon a time had 2 different parents, now they share the same parent, they're part of the same component. In a graph, this might be, let's say you have 2 different components and you add an edge between 2 nodes in 2 different components, right? That's what creates that union and puts it into the same component with the same parent. All of those nodes will have the same parent in that case. So words are less useful than pictures. Let's look at an example. So here we have a disjoint set, right? There are 3 different components in this graph. There's the A, B, and C component, right? And right now it's just nodes with no connections, right? There's no edges between them. It is 3 different nodes. They are not connected. So as I said, A is in its own component, component 1, B is in its own component, component 2, and C is in its own component, component 3. Okay, so we have a disjoint set, right? So let's talk about those methods. What would it look like to, let's say, call union, right? So here we have union BC. We're trying to make a connection between B and C. Now, B's parent is B, obviously, right? There's only one node in that component, and C's parent is C. So union is somehow going to make their parent be the same, right? So here we add that edge between them, and now you can imagine C's parent is B and B's parent is B. Or we could have done it the other way, right? C's parent is C and B's parent is C. Doesn't matter. But now, instead of having 3 disjoint sets, we actually have 2, right? Or 1 set. I'm not actually sure if like the component is the set or the whole thing is the set. I don't know. Leave it in the comments below if you do. But we have 2 components instead of 3 components, right? Now, the other method we talked about was find, right? And we said find just returns a component's parent. A node's parent, right? What component does this node belong to? So if we call find with node C, we're going to expect the node B to be returned, right? Because B is C's parent. And here we go, it's B. So I hope that makes sense. It's actually a pretty simple concept when you stop thinking about all of the different ways that you can do this in code and just think about it in terms of concept, right? Like, oh, okay, different ways of grouping different nodes and then creating those groups between them. So, question of the hour, how do we represent this in code? Elizabeth, you've told us all about the concepts. It seems very simple, but something is telling me that there's a little bit more to this, and it's not going to be so simple in code. And you'd be sort of right and sort of wrong, right? I think that the thing that trips people up here is not understanding the purpose of what we're doing. So I hope to try and clarify that here and make it, continue to be a simple concept. So the thing to remember is that we have our graph, right? We've have our nodes, we have connections between them. And what we want to do is kind of look at this graph through a new lens, right? Through this disjoint set lens. We want to see what are the components at play here? How can we play with the edges and play with the connections between the nodes so that we can organize these nodes into groups and come to some conclusion, right? We forget about any sort of problems. There are many different, use cases for this kind of approach. But for now, just try and remember that the disjoint set is going to be a lens through which we're looking through that graph, right? So how do we represent this in code? Let's take our example from, a couple slides ago. We have our 3 different nodes, right? This is a disjoint set. We have 3 different components. We have the 0th node, the first node, and the second node, right? All 3 of these are their own parents. They belong to themselves. There are no connections at the moment, right? So you might get this graph in code as an adjacency list, right? And you would get a graph with a dot nodes property. And in that nodes array, you would have all of these nodes. And in those nodes edges lists, there would be nothing, right? Because they're not connected to each other. You could get this as an adjacency matrix, right? If you remember, that was an array of arrays where each array, the index represented what node we were talking about, and the actual array, each index of the subarray was either a 0 or a 1 to denote a connection to whatever node is at that index in the graph, right? This is all review. So again, we'd get in an adjacency matrix, let's say, we'd get an array of 3 arrays, right, to represent the 0 node, the 1 node, and the 2 node. And it would all be zeros, right, because there are no connections. So just remember, that would be how we would represent this graph. How would we represent this disjoint set, though, right? So we can use an array to do that. And I don't want you to confuse this array with all of the arrays that I just mentioned, right? The edges list, the adjacency matrix, whatever. Again, this is a lens through which we're looking at the graph. So in code, we could represent the disjoint set as an array where each index represents the node at that index, right? So the 0 node would be at the 0th, which is, this -1, and I'll explain why there are -1s here in a second. This first node would be at the first index, and this second node would be at the second index, right? And we're going to use this array to track the different components. So what are the rules of this array? So each index represents the node, right? As I just said. Each value represents the node's parent, okay? So that means that whatever's at each index, that's the parent of the node that that index represents. Okay, so what's a -1? A -1 denotes that that node is its own parent. So here in this graph, at the 0th index, right? -1. Okay, so 0 is its own parent. 1, -1. 1 is its own parent. 2, -1. 2 is its own parent. Does that make sense? I hope so. Okay, so we have an array of -1s. Big whoop. What do we want to do here? We want to see union in action, right? That's going to be how we start to form our components in our graph. So let's implement union. So we have our graph like we had earlier before, right? We have our array. This is our disjoint set. This is the representation. And you'll remember that -1 denotes that each of these nodes is its own parent, right? So how do we do a union? Let's do a union between node 1 and node 2. So the rules of union. First, we need to check, are these two nodes in the same component, right? We can't perform a union if they're already in the same set. There's no point in that, right? So the first thing we do is check, do these two nodes have the same parent? We can easily do that by looking at the array, right? And seeing, do these two nodes have the same value as a parent, right? Now, remember, if they both have -1s, that doesn't count because that means that they are each their own parent. And that's what the negative denotes. So this would only be true, let's say, if 2 already had a parent of 1 and 1 also has a parent of 1, right? So we'll see that in a second. But the first thing before we union anything is check to see, are these two nodes already in the same component? If they're in separate components, we make the parent of the second node the same parent as the first node. And this is arbitrary. We can actually make the parent of the first node the same as the parent of the second node, right? We can pick whatever we want. We can do it based on how the sizes of each component, right? Make the node that is in the larger component the parent of the node that's in the smaller component, right? You can do all sorts of things. But essentially what you want to do is you want to make them have the same parent. So in our case, we're going to make the parent of the second node the same parent as the first node. To take it a step further, we can track how many nodes are children of that parent node by adding the initial value of the second node to the value of the parent node. Now, what does that mean, right? What are all those words? All that means is that as far as we've, talked thus far, -1 denotes that that node is its own parent, right? What about the rest of the negative numbers? Why don't we use those too, right? So what we can do is before we call union, we can grab hold of the value of that second node, right? And that second node is going to be, we are going to take the size of the component it belongs to, and add it to whatever node is becoming the parent. And so it's not only that a -1 denotes that that node is its own parent, but a negative anything, right? And then the number afterwards we can use it to track the size of that component, which we're already doing by using -1s, right? Each of these components are their own parent, right? The node is its own parent, and they're each of size 1. So let's have an example here because I think that will, hopefully illustrate this point a little bit better. So let's say we want to call union for between the two nodes 1 and 2, right? So the first thing we do is we need to find, right? And what does find do? Find is going to return the parent of every component, every node, right? So we're going to call find on 1. What's 1's parent? It's 1. right? -1. So this is going to return 1. Then we're going to call find on 2. 2 is also going to return that 2 is its own parent, right? And 1 does not equal 2, right? The parent of 1 is 1, the parent of 2 is 2. Those two things are not the same, right? That's this step where we're checking, is the parent of the first node the same as the parent of the second node? If it isn't, we can take the value, right, that's at that second node, which is -1, and we can add it to the value of the parent of the new parent node, right? Because right now, -1 symbolizes that that component that 2 belongs to is of size 1. And we can add them. So this will become -2, right? Because now 1 is a parent of 2. So its component is a size of 2. And then 2, its new parent is 1, right? So instead of -1 here, we'll set it to be the first node, right? So that's just going to look like this. And as you can see, it ends up becoming this kind of, it's a two-dimensional array, or it's actually just a single dimension of an array, right? It's just a collection of numbers, but we're using the different values to denote different things, which I think is, very cool, but also a place that people get, stumble and get caught up in. So I think it's important to understand that we're just like, we can do whatever we want, right? So these are the rules that we're setting up so that we can store all of this information in just this list of numbers. So I'm going to show you this in code, and I hope that it will become a little bit even more clearer, what's happening here. And we can also walk through a little bit more of a detailed example, a larger example than just, 3 nodes in one union, so that we can really practice these, this find and this union methods, so that when we go to implement it in code, it's obvious how we do this. Let's walk through that slightly more complicated example so we can really see how you might use the union and find methods to organize the different nodes in a graph into different components. So here you'll see a slightly more complicated graph, right? There's 5 nodes, there are a bunch of connections, there's even a cycle, right, between nodes 2, 3, and 4. This is going to become important at the end. You'll see where we'll use this disjoint set and all of its methods to determine whether or not there is a cycle, but we'll get there. So we get this graph, right? And right away, we're going to make a disjoint set out of it. Let's initialize it that all of these nodes are in their own components. We have 5 different components. Each of these nodes are their own parents, right? And this is going to look like this. It's going to be in an array of length 5 with -1s at each index, each -1 denoting that that node at that index is its own parent, and it's in a component of size 1, right? It's the only node in that component. Okay, cool. So let's slowly, one by one, add these edges back in, aka we're going to be calling union, right? That is the act of connecting 2 different nodes and creating one component where there were 2, right? So first, let's add this edge between 0 and 1. Now, I'm adding these edges kind of, arbitrarily, right? You could start with any of the edges, but I'm just picking this one. Depending on the problem, you will add edges in different ways. So that's just, for you guys to understand that I did pick that randomly as our first node. So we're connecting 0 and 1. What does that mean? We are going to call union on 0 and 1, right? Now, if you remember, when you call union, the things that you do first is find the parents of each of those nodes, right? So we call find on 0 and we call find on 1. Now, find, if you'll remember, uses this array to figure out where is the parent of the node that you passed in, right? So find 0, we go to the 0th index, which is right here, and we see a negative number. So the negative denotes that it is a parent itself, right? So 0 is a parent. So 0 is its own parent, right? And then we call find on 1. Find on 1 is right here, same thing, right? Negative. It denotes that it is its own parent. So 1 is its parent. Now, when you call union, the steps, if you remember, are that you add the number of the second node to the number of the first node so that we can keep track of how many nodes there are in a component, right? So that will look like this. We'll say, okay, so this is the second node, right? So -1, let's add it to -1. So this is going to become a -2, right? And then what happens to this -1? So we want to make 1 have a parent of 0, right? So we can just swap that out for a 0. And let's see that that is, in fact, how this works. And it is. So here we see that at the 0th index, we have a -2, which denotes two things. Number one, that it's a parent, right? And number two, that it is a parent of a component that has 2 nodes in it, right? That's what that the 2 represents. And then at the first index, we see that 1 has a parent of 0, right? So that's kind of how that array works. And let's continue adding these edges. So the next node that the next edge that we are going to add is going to be between 2 and 3. And again, I chose that randomly just to, show you guys how you can make the different components. Depending on the problem, it will be different how you go about doing this. But we're going to add an edge between 2 and 3, call union on 2 and 3, right? So the first thing we do, we find the parent of 2 and we find the parent of 3, right? So let's go to our array. This is our new array, right? That's tracking our disjoint set. So 0, 1, 2. 2 is its own parent. Cool. Find 3. 0, 1, 2, 3. 3 is also its own parent, right? So this one is another easy one. We basically do the same thing as before, right? Where we add the value at the second node, right? So that's -1. We're going to add it to this one, which is the new parent, right? So that's going to become -2. And then -1, now this represents that third node, right? So instead of a -1, this is going to point to its new parent, which is 2, right? So let's make sure that that is exactly what it is supposed to be. And it is. So this array, you can see we now have 2 components where they have the size of 2, right? And then we have a third component, which is this one, right? This is 4, and it still is just its own parent, and it is the only one in its set, right? Or in its group. Okay. So next we'll add an edge between 1 and 2, right? That's this edge right here. So we'll call union on 1 and 2, right? And we will find the parent of 1 and we will find the parent of 2. So let's go to our array, right? So 0, 1, okay. 1's parent is 0. Cool. Okay, 2. 0, 1, 2. 2 is its own parent, right? So let's see. Okay, perfect. Okay, so what are our rules here? We need to add what's at the second component, right, to whatever the parent is of the first component. So this is -2, right? So we are going to add it to 1's parent, which is 0, which is over here, -2, right? So now instead of a -2, we are going to get a -4, right? And then instead of 0, 1, 2, instead of this being a parent, it is no longer a parent. We are going to set it to have a parent of whatever the first node's parent was, right? So that's 0. Okay, perfect. So let's see. And that is exactly what we get. So now we have 2 components, right? We have 1, which is size of 4, right? And the ones that point to it are the 0th, which is the parent, the first, right? The second, right? These both point to 0. And then this third one, which points to 2, which points to 0, right? So you can sort of see here, this is a little bit like a linked list, right? Like each of these are not necessarily going to have values of 0, but whatever values they do have, eventually at the end of the line, the parent will be a negative, and that will be 0, right? That's going to be the one that is the parent. In this case, it's 0, not always 0, but whatever. So I just want to make sure that you guys see that just because it's all in the same group doesn't mean it's all going to have the same value. It actually might point to a different node that then has a value of the parent. So that's something to keep in mind. Okay, So the next edge we're going to add is going to be between 2 and 4. All right, so union 2 and 4. So we're going to call find on 2 and find on 4, right? So let's go to our array here. Let's see, 0, 1, 2. 2 has a parent of 0. Excellent. Okay, 4. 0, 1, 2, 3, 4. 4 is its own parent, right? Okay, cool. So what do, right? This is going to be, again, the same. We are going to take the value of that first one, right? Or the second one, excuse me, that's -1. And we're going to add it to the parent of the first one, which is 0, right? So that's -4 here. So we can cross that off, make that 5, right? And then this is going to have a value of the parent of the first one, right? So that is 0 in this case, right? So let's just make sure. And we have that array, right? So now we have actually only one component, right? We have one component with 5 nodes, and they all have the same parents in the end, right? This is the one that it has a parent of 2, but 2 has a parent of 0. Okay, so what can we do now? We want to add that final edge, right? Between 3 and 4. So let's see what happens when we add that edge between 3 and 4 in this disjoint set situation. So we call union on 3 and 4, right? We find the parent of 3. So let's see, we find the parent of 3 and we find the parent of 4. Okay, so the parent of 3, 0, 1, 2, 3. Okay, that's 2, right? So 0, 1, 2, that's 0. Okay, so 3 has a parent of 0, ultimately. 4, 0, 1, 2, 3, 4. 4 also has a parent of 0. And I hope that you see where I'm going with this. This means that we have a cycle detected, right? Because we're trying to union two things that already are in the same component. So if you ever have two different nodes that you are trying to call union on that already have the same parent, then you can return that there is a cycle in this graph. So this is kind of just one way that you can use this sort of new way of thinking about graphs, right, in these different groups, components, disjoint sets. And it's a way of determining things, right? You can ask yourself, what happens if I connect these two nodes to each other? How do the groupings change? How are the nodes interacting with each other, connected with each other? What are the sizes of these different components? Stuff like that. So I hope this is exciting to you, as exciting to you as it is to me. Next week, join me. I will be coding all of these methods we've talked about, union, find on disjoint sets. And then we will also talk about how are we going to use this to solve our actual problem, right? That malware problem. Just to give you kind of a, hopefully get you interested, get you excited. Essentially, what we're asking in that malware problem is tell me about the different groupings of these nodes, right? There's this grouping that got initially infected. That might be a component. There are other parts of the graph that are components. And as we add different nodes to the different components, how does the entire network change, right? How do these components grow in size? And how can we minimize that size after adding components that have malware in them, right? So stay tuned. Definitely check back for next week's video to see an implementation of all of this in JavaScript. I hope you enjoyed this. See you next week.